Right, so this is number 15 off of your review. Okay, almost there. What we're going to take a look at is the question's asking us to look for where the new point is going to be, given that we have the original function y equals f of x, and we want to know where that new point is going to fall or change to, given the new function at the bottom, y equals 3 times the function of -4 times x plus 1 minus 2. The way we're going to tackle these questions, in particular with just one point, you could use this method with any of the graphs. You just have 5 points, and you could use the method we're going to discuss here to transform those 5 points into the final graph. No problem. That method that we've discussed is what's called the mapping statement. And what the mapping statement says is we're going to take the original function, right? We're going to transform the original function's points using this mapping statement. Okay, and what we need to do is identify information that's strictly affecting x and information that's strictly affecting y. And what we're going to do here, I'm just going to highlight it. Information highlighted in yellow corresponds with vertical work, okay, and affects the y values. Anything highlighted in blue is horizontal work and ultimately affects the x values accordingly, okay? And so what we're going to do is we know when I look at this, anything in blue is going to be horizontal. So what's going to happen? Well, we're asking ourselves, when I look at the equation or the transformations that have happened to the function, what's affecting what, right? So anything on the inside is horizontal and affects x. So we're going to attach it to the x. So let's deal with that negative that's there first. That negative that's attached to the 4 controls the fact, or it affects the graph in a way that it gets reflected over top of the y-axis. Okay, it's a horizontal reflection. So that must mean all the values of x that are on this graph are going to become negative. Okay, so we're going to go negative x, but there's also another component on there. It's the 4, which we have to take into consideration. So we know if I see the 4 and I use the word horizontal stretch or compression, it's always opposite to what I think it's going to be. So I see the 4, so that's going to make it, what's going to happen? Well, we're going to horizontally compress the graph. What does that mean physically? It means that the x values are going to become a quarter as big. So we're going to take them and basically divide them by 4 or multiply by 1/4, right? X. Now the last piece here that's in blue on the inside of the function says to the graph would have moved to the left 1. Remember, it's opposite. The only way to get a graph to move 1 to the left would be if I took the original x value and subtracted 1 from it. Okay, again, everything is about this oppositeness, right? So that's how the x's are getting affected. We're going to do the exact same thing for the y's, right? It looks like on the outside, the yellow components are vertical, and it looks like I'm taking my y values and multiplying them by 3, and then I'm taking the whole graph and moving it down 2. Okay, when I move something down, it doesn't affect the x values, which is why we've separated it out the way we have. Okay, so this is what your mapping statement says. Now, if I want to, just in words, if I want to transform, right, the 0.14, which is what this is telling me, I'm going to transform it using the mapping statement we've just created. And the mapping statement's telling me to go -1/4 times whatever the x value is that I'm looking for. In this case, it's 1, or what x value I've been given, and then -1. And then the y value is treated separately. We're going to go 3 times 4 minus 2. So now I can just do some math, right? So we're going to get this transforms into -1/4 minus, well, we can do 1 is just going to be -4/4 if I were looking for a common denominator, as I need to, and then 12 minus 2. So we get -1 take away 4. All right, transformed point. When I use this mapping statement, or we apply the transformations to this point, we're going to get -5/4 and 10. Okay, so when I apply the transformations to the original point, 1, 4, it spits out -5/4 and 10 as the final transformed point, given the transformations on the function.